Hi, welcome back. In this lesson, we are going to look at Fourier series, part 1. The Fourier series can be used to represent a periodic signal, such as the one given below. It's a square waveform, periodic square waveform. Periodic signal as a weighted sum of harmonically related cosine and sine waves. So what does this mean? So fundamentally, you have this signal given here, which is a square waveform in this black color, and we can find the fundamental frequency of this signal, which is in red color here, and then we can find the third harmonic. Second harmonic is going to be 0 here, and the third harmonic is the one given in green color, and as well you can find the fifth harmonic, which is given in this uh, orange color. So when you add the first harmonic or the fundamental, the third to the fifth, you get this blue color one. So basically what you got here is actually a signal which is closer to the original square waveform. If you had used only one fundamental frequency, the first component, you get something like this, which is not very similar, but it just follows the frequency zero crossing points. But if you want to get a closer waveform, you need to add fundamental to the other harmonics. In this case, third and fifth are present, so you can add those and get this one. Actually, we can add many more harmonics to come up with a signal which is closer to the original square waveform. So if you add up to 9 terms, we can get something like this. So which is a bit closer to the original square waveform. So this is the pictorial view. Let's see how the mathematics behind this. The mathematics says that for a periodic signal, GPT may be written as P is for periodic and T is for time domain. So G, any signal G, periodic signal in time domain, can be written as A0 plus 2 times sigma of 1 to n equal to 1 to infinity an cos 2 pi nt over t0. T0 is the periodicity of the signal, which is a periodic signal, plus Bn times sine 2 pi nt. Again, T0 is the periodicity of the signal, where An and Bn are the amplitudes of the cosine and sine terms, and T0 is the period of the fundamental frequency of 0, which is equal to 1 over T0. These cosine and sine terms are also called the basis functions. And let's look at the basis functions. These basis functions form an orthogonal set over the interval t0. That is, they satisfy the following conditions. When you multiply those two orthogonal functions, cos and cos, and integrate from k to k plus t0, we get t0 over 2 if m is not equal to n. If m equal to n, this will become 0. That is the condition of orthogonality. And when these two functions are different, when you take cos and sine, obviously for all values of m and n, it should be 0. And if you multiply these two sine terms, we should get t0 by 2 when m equal to n, and 0 when m is not equal to n. So these are called basis functions. Also, for the special case, we had in this previous example, we saw a letter k there. K is any constant. In the special case, we can put k equal to negative t0 by 2. So that is when you work out examples, let's see how it goes. So just for the moment, is just remember that k can be negative t0 by 2 for most cases. The coefficients are derived as follows. Actually, we had to find out 3 coefficients to get that expansion. Fourier series expansion. So A0 is the average value of the signal, 1 over T0. T0 is the periodic value, integrate from k to k plus T0. So k can be negative t0 by 2. So then this function will go from negative t0 by 2 to positive t0 by 2, which covers one periodic of the periodic signal, one period of the periodic signal. So it is in this case GPT, we don't know the signal, and dt is the integral coefficient here. And then we can calculate n. Again, there's an expression for that one. N equal to 1 over t0 integral of k plus t0 GPT cos 2 pi nt over t0. This is again a definition. Let's see how we can simplify this one later. That n is actually for 1 to n, 1 to up to infinity, n here. So there's a n here. And also we can write for bn 1 over t0 integral k to k plus t0 GPT sine 2 pi nt over t0. T0 is the periodic value of this signal. Actually, the values that you got here are the values that we saw earlier in the expression GPT A0, AN, and BN. So once you calculate A0, AN, BN, and BN, we can write an expression for GPT. So let's take an example here. To obtain the coefficients A0, AN, and BN for the following square wave form, we are going to do some mathematics here again. The functions is actually this the periodicity. You need to look at what is the periodicity. T0 is a periodicity which is actually going from minus t to plus t. So actually, even though the function does not exist here and here, the periodicity you should take from here to here. That is negative t to positive t. Again, positive t to upwards. You can see a similar pattern there. Now what we do here is we are going to apply the first expression where a0 equal to 1 over t0 k to k plus t0 gpt dt. So now we can see k actually in this particular case it will go from minus t to plus t because our t0 is 2t, t0 2t, and k is equal to t0 by 2. So t0 by 2 it can from minus to plus. So when you substitute t0 by 2 equal to 2t, and you get the limits are minus t to plus t gpt dt. So now we substitute the value for GPT. GPT is the periodic one period of the periodic signal A, and we can integrate it from minus t by 2 to plus t by 2 because the function does not exist. If you look at back here, so the function only exists from here to here. So therefore, from here to here, the integration is 0, and minus t by 2 to plus t by 2, you have value of a there. So that's how you can write here. Instead of GPT, you write a, and bear in mind here, please note this one, minus t will become minus t by 2, plus t will become plus t by 2, because outside t by 2, the function a is equal to 0. And then when you integrate a with respect to t, you get at minus t by 2 to t by 2, at 1 over 2t is the coefficient here. And now we simplify by substituting t by 2 here. T by 2 minus t by 2 become t by 2 plus t by 2. And then we can simplify to get the answer for the average. This a0 is called the average value of this function, which is equal to a by 2. This function has an average value here, a by 2. And now we'll calculate the value an. An is given by 1 over t0 k to k plus t0 gpt cos 2 pi nt over t0 dt. N is 1, 2, so on and so forth. So now we substitute again for GPT. GPT can be substituted with capital A, and this part still remains same, but we need to look at the the function a only exists for minus t by 2 to plus t by 2. And now we integrate this one A is a constant. Cos can be cos 2 pi nt over 2t is like cos alpha t. So when you integrate cos alpha t dt, it will become sine alpha t over alpha. So alpha is equal to 2 pi n over 2t. So you substitute it here, a over 2 pi n over 2t, and cos will become sine, and the limits are minus t by 2 to plus t by 2. And you can further simplify this one by substituting values here. 2 pi n, you can take it upwards. So basically you get a times a over 2t times 2t over 2 pi n. And then we substitute for this one, sine 2 pi n 2t, t will be t by 2 minus sine 2 pi n t minus t by 2 will come here. So then this minus and this minus will uh, become positive there. So therefore we got here sine pi n over 2, t will go off, sine pi n over 2 plus sine pi n over 2. Therefore in this next slide we can see it is 2 sine pi n over 2, and this is the function that you got earlier here, that is the coefficient. And then now we simplify this one to obtain a function like this. So whenever you see a function like this, we can either replace it with sinc function. Basically sine pi n by 2 divided by pi n by 2. Earlier it is pi n by 2 only. We can have a denominator and then find out the how you distribute the remaining term. So there's a half missing, so basically half will come out there. And this term, as we have seen just now, is sine n by 2. And since the given square wave form is a symmetric function over x-axis, Bn is 0. So what we did so far is actually calculated the values of a0 and an, and the value for Bn cannot be value for Bn equal to 0 for this particular expression. That is the answer to this Fourier series expansion. Thank you.